So you're looking at the Heathkit model PS3 regulated power supply. These particular regulated supplies, of course, were vacuum tube based. Vacuum tube regulated supplies were something that probably stayed with us till about the mid-60s. And at that time, we had solid-state power supplies taking over in a big way, especially when the 723 chip arrived on the scene. When the 723 came along, solid-state regulation became possible. And of course, high voltage wasn't needed as much with solid-state, so generally, regulated supplies from the 60s onward, they were below 100 volts. Now we want to return to working with vacuum tubes, and we need high voltage again because we're building audio amplifiers, both hi-fi and guitar amps, and also we need regulated power supplies for our RF circuits, various variable frequency oscillators, transmitters, and so on. This Heathkit supply is in demand again, and you're finding some pretty high prices for them on eBay and even at some of the hamfests. I am going to take this one apart. We'll take a look, see what's inside, and we will go through the circuit carefully so we understand how the regulator works. These are nice because they have the onboard transformer and rectifier, and they produce a high voltage around probably 600 volts, and then you have the regulator part of the circuit, which takes that 600 volts down to 0 to 500 volts. The pass devices aren't much different than transistors in that the more the differential you have across the device, the more dissipation in the pass device. So you'll find that with these, as you increase in voltage, the amount of milliamps that you're drawing goes down. You're not able to support, for instance, 500 milliamps of current at high voltage, but you might be able to at, say, 20 volts. So that's the way that works. So let's take a look inside. Let's see what we're looking at here first. And by the way, I am going to do a variable regulated power supply based on solid-state circuitry. We're going to build one of these. We're going to build a modern version of a high-voltage variable regulated power supply. It should be a fun project. So we'll start working on that project in the next video. But for now, let's see what's going on with the tube-type regulated high-voltage power supply. So obviously, this power supply came out of an industrial environment. It's got markings all over it. And we can see the Heathkit cord. This is typical from, early 60s, late 50s type Heathkit stuff. You had your regular two-prong plug and a grommet, for the line to go into the kit. Oh, was it a kit or was it commercially wired? I guess we're going to find out pretty quick, right? It's always exciting when you open a Heathkit. The commercially wired ones look a little different than the ones that you build with your dad in the shop. So we'll see what happens here. Okay, it fell. Is that it? Is that all you need to do? Maybe. See if we can get the case off with just 2 screws. That'd be kind of cool, right? Yeah, seems to be coming along. Okay. The transformer is the heavy part. Okay. Pretty neat looking, right, from the top. Couple of voltage regulator or VR tubes. Here's our 2 pass devices. These are the 1619s. Again, these are like 2.5 volt filament type 6L6s. They do not have a cathode. Over here, this looks like a rectifier tube, another rectifier tube, and the control tube. This is the magic control tube, a 6SJ7 pentode, I think we're talking there. Okay, so that's everything you need for a high voltage regulated power supply from the top. Pretty heavy transformer. Let's look at the bottom. Maybe we can determine if this thing, well, let's see if it will go on its head without breaking something. Oh, it did. Okay. Does it look like it's factory built or if it's built as a kit? Usually you can tell. I'm going to say this probably was a kit because I can see leads not completely dressed. Now it's been repaired too. These have been replaced. These electrolytics have been replaced. I think it's a kit, but it's been very well wired. Black wires. Don't be looking for no color code here. These are some high value resistors and these tend to drift. I did check to see that everything was discharged, but it does have a bleeder resistor, so there's no fear we're going to get a shock. A little bit of discoloration here. That could be from the last capacitor that was here, or it could be something leaking out of the transformer. Hard to say. Okay, it doesn't look too bad. So, because of our drift issue, we need to check the values of all the resistors, see where they're sitting. And then we'll look at the schematic. So next, let's go into the circuit. Let's find out how this thing works. You know, I'm not just going to blindly go in here without understanding what the circuit is. Obviously, these electrolytics need to be checked. I'm looking at them to see if we got any bubbling. They're all quite old. These are all going to be from the 60s. So probably all of these capacitors should be changed out, but I'm not going to judge. Let's go through the circuit first, and then we'll decide if we need to change something out. I guess high voltage with solid state was still a fairly new idea in the late 70s. The early models covered 50 volts to around 300 volts. The PS3, introduced in June of 1954 for $35.50, offered regulated B+ voltage control from 0 volts up to 500 volts DC. The transformer high voltage AC was rectified. It used two 1619 tubes as series regulators. Two 0A2 150 volt VR tubes provided a stable reference voltage. A 6SJ7 pentode was used as the control amplifier. This voltage regulator provides a constant DC output voltage despite variations in the input voltage, load current, and it even compensates for rapid variations such as noise and ripple. A second rectifier tube, a 6X5, was added to provide a negative 150 and 300 volts to allow the series regulator tubes to operate all the way down to 0 volts. So this is an early use of bipolar power supplies, but really it's referred to as negative bias since this bias supply is at very low current. The PS3 remained available to order from Heathkit until 1960. Okay, let's look at the specifications next. The PS3 basically supplies 130 milliamps at its lower voltage, and that falls, however, down to 10 milliamps once you get up around 500 volts. This is because of the voltage drop across the regulator tubes. It starts to get into the dissipation factor of each tube. There are two slide switches, one marked power and one marked standby. The filament output binding posts show the maximum current for the 6.3 volt supply as 4 amps AC. There is no center tap on the AC output, which was meant to drive filaments for typical tubes. The high voltage supply is a conventional full wave with a transformer secondary, and the 5V4 rectifier followed by a simple capacitance filter. Notice they have two capacitors in series, but there's no equalization resistors. I would have put resistors across these to equalize these capacitors. I'm surprised this worked. Also, notice the standby switch. It's grounding the center tap of the transformer. This is kind of a handy way of turning high voltage on and off. The standby switch is double pole. It also
disables the negative bias supply when you're in standby. The connection to the output terminal is through two tubes, the 1619s. Think of these tubes as a variable resistance under the control of the 6SJ7 tube's grid voltage fluctuations. The 6SJ7 is connected so that variations in the output voltage will control the grids of the 1619 pass tubes. So you can see we have the common line here. This is your B minus, your common. This is the plus line here. Between the B plus and the negative voltage, we have this voltage divider. The voltage divider goes to the control grid of the 6SJ7. The 6SJ7 is connected so that variations in the output voltage will control the grids of the 1619 pass tubes. Since the 6.8 megohm resistor is a plate load, and it's common to both the input and the plate of the 6SJ7. Manual control of the output voltage is accomplished by varying the normal grid bias on the control amplifier tube via the 500K voltage control potentiometer. There's also a negative voltage supply. This 6X5 basically hooked up as a half-wave rectifier. They're attaching to one side of the center tap transformer. So they're rectifying the opposite direction on the AC swing. It's going into a simple filter, and then the two OA2 150 volt regulators. So it's 300 volts total here. They center tap it with this potentiometer, so this is roughly, around 150 volts. It is adjustable. This supply then produces two voltages, one regulated at 300 between B minus and this point, and then effectively a center tap type adjustment. The negative 150 regulated power connects to the cathode of the 6SJ7 control tube, allowing the tube to operate even with a plate voltage near zero. This negative 300 volt supply provides a reference for the control tube as well as a return for the output of the series regulator. If you were to dispose of this negative voltage, you'd be very limited on your range in the output. You might be able to get between 50 and 500 volts, but you certainly couldn't go to zero without a negative voltage supply. Here's a couple other schemes you can use to do this. A voltage divider system where you bring ground up on the voltage divider and call that your B minus. That makes an artificial negative voltage, which would work. Let's look at the series regulator circuit closer. A pair of triode connected 1619 tubes. Notice the screen grid is connected directly to the plate on both of these. These are wired in parallel and are used as a series regulator. These tubes drop the 600 volts at the input at no load from the B plus power supply to the desired voltage set by the front panel B plus output control. The tubes act as active resistors, keeping the voltage on their filaments constant as the current drawn through the tubes fluctuates. These tubes are controlled by the control amplifier tube. Two series 150K resistors act as 2-watt bleeders. They're connected in series from the filaments to the minus 300 supply. This assures a minimum current draw and safe discharge path. The heart of the regulator is the control circuit. The cathode of the 6SJ7 control tube is connected to that adjustable voltage that's off the minus 300. And the screen is connected to the voltage divider that's connected to the input or the source voltage. This is interesting. When you think of a tube that has three grids.
One of them, she wrote, the inconvenience is exceeded only by the dirtiness.
Pentode has three grids. You have the suppressor grid, you have the screen grid, and you have the control grid. In reality, all three of these grids are control grids. We know that if we messed with the suppressor grid, we could modulate the tube. We know that if we mess with the screen grid, we could modulate the tube. And we know if we mess with the control grid, we can modulate the tube. Now I say modulate. What we're modulating is voltages. And we're making this tube more or less conductive. If the voltage goes down on the input to the regulators, it's sensed on the screen grid. That actually turns the 6SJ7 off almost as effectively as the control grid is turned off by the negative feedback from the output. So we're sensing the input and we're sensing the output, both of which can control the 6SJ7's conduction, which directly control the resistance of the 1619 pass tubes. Any change in current through the control tube changes the output voltage. This is negative feedback. When the load draws a larger current, the B+ terminal of the power supply tends to decrease. This is sensed by the voltage divider across the output, and the potentiometer's wiper feeds pin 4 of the 6SJ7, thus putting a more negative bias on the control grid. So the 6SJ7 turns off. The 6.8 meg pull-up applies more positive bias to the control tubes, lowering their resistance until equilibrium is again restored. So that's the feedback loop, really a double loop. We have the input and we have the output, both contributing to a negative feedback loop to control the two pass devices. So again, a voltage divider chain made up of the control voltage potentiometer and two fixed resistors is connected between the -300 volt source and the B+ output voltage. The potentiometer in the center of the chain is the B+ output control. Its wiper connection is filtered by a 0.1 capacitor. This is really interesting. This can actually fight some of the noise and ripple at this point, further improving the regulation on the power supply. So this is negative feedback. The grid of the control tube senses this and changes and adjusts the series regulator tubes to return the voltage to the set value. Additionally, the screen grid of the control tube is connected via voltage divider to the raw B+ voltage. Thus, any sag in the raw voltage is also detected by the control tube. This divider is basically controlling the output impedance of the power supply. It's set to make the impedance close to 0. The output impedance is specified to be less than 10 ohms from 1 Hz to 1 megahertz. There's also a metering circuit. You'll notice there's a shunt resistor of 9 ohms. This is for sensing current, or milliamps. And then we have the meter that we put in the voltage, positive on this side, and now we're measuring voltage through the meter. So we can selectively monitor the output voltage or the B+ current draw. The shunted current meter is 150 milliamps full scale with a series resistance of 0.66 ohms, and it's placed in line with the B+ output. No provision is provided to monitor the negative supply since it's very low current internally.
So some of you are wondering, am I just going to button this up and send it back to my buddy who lended it to me for the video? Well, no, I never do that. I always like to return something in better shape than when I found it. So I'm looking at the bottom here, and I can see these capacitors are definitely originals. This was built probably in the late 50s, early 60s, so it's the end of the era. There are some substitutions in values on some of the parts, so those are probably some mods in the kit that happened in the latter part of the design. These two are definitely replaced. You can see the tubing. Only a qualified technician would go that far as to put tubing in there. So these two have been replaced. So I probably am going to do some capacitor changes. I'll change the two capacitors on the input. I'll probably put in some low-cost 100 mic, 450 volts. That's going to give an equivalent 50 microfarads of capacitance, which is 5 times what they used. You have to be a little careful sometimes, but that's on the primary side, so it should be okay. This is before the regulator, these 200 mics I'm putting in. I will put some sharing resistors across them, maybe some 1 meg resistors, something like that. And then these smaller guys are going to be for the output to replace these two. Now, the most important capacitor in here, beyond the electrolytics, is this capacitor. This capacitor is the 0.1 mic filter cap. That's the guy that picks up any ripple or any noise, feeds that back to the control amplifier, and it actually can adjust for those and null them out. That's an important capacitor, just like the automatic gain control capacitor in an old receiver. If that's leaky, your AGC doesn't work right, well, if this guy's leaky, it could affect your regulation, it could affect how good ripple response is, and so on. So I will replace this 0.1 microfarad capacitor. That's about as far as I go before I test it again. Then we'll look for that problem we had where the voltage was slowly going down. Now, I might have been over dissipating the tubes. I kind of willy-nilly put it out at 150 volts at 100 milliamps. That's probably beyond the rating, and that's mostly because of the dissipation of the two pass tubes. The pass tubes, the 1619s, are limited in dissipation. The two things you have to worry about with pass tubes are the dissipation of the tubes and the input to output voltage rating. A lot of pentode tubes are rated at 200, 300, 400 volts. Well, we have 600 volts on the input here, and we're trying to go down to 0. So that's not going to work very well with most tubes. So we want to have a tube that has plenty of headroom on the high voltage side. Perhaps a pair of 6 DQ6s would take the place of these tubes and give you a little more current capacity. It's not the transformer that's limiting your current. It's the dissipation of the tubes. So a pair of 6 DQ6s would work great. The only thing you have to be careful of is the screen grid rating. A lot of those fancy beam power pentodes, beam power tetrodes, they had very high plate voltages, 700, 750, even up to 900 volts DC. But then when you look at the screen grid, it's only rated at 200, 300, 400 volts. So you would have to put a series resistor to the screen grid if you're going to triode connect. I would suggest something like a 15K resistor between the screen grid and the plate to save the tube. So how would you power a pair of 6 DQ6s? Remember, the pass tubes here run on 2.5 volts, and 6 DQ6s would need 6 volts. Well, you'd have to give up your 6-volt output and dedicate it to powering the 6 DQ6s. It's a little bit dangerous to still bring the 6.3 volts out to the front panel because now you have a cathode that's at very high voltage and you have a filament that's essentially at ground. That would be too dangerous to bring out to the front. So unfortunately, you're going to lose your 6.3 volt front panel connectors if you use something like 6 Y6s, 6 DQ6s, 6 DQ5s, 6080s, some other type of pass tube. You have to fool around with that screen grid and figure out if the tube can handle the worst case condition, which is highest current at lowest voltage has the highest voltage drop across the tube. You can very easily exceed the plate voltage rating or the screen grid voltage rating. Okay, let me do my work and then we'll come back and see how this thing acts. I have done the capacitor changeout. Here are the two capacitors for the negative power supply. 33 microfarads at 450 volts. So that's a slight increase from the 20s that were there. And here's the pair of 100 microfarads at 450 volts, replacing the original 20s. And here's my equalization resistors. So it looks like I put 1.5 megs in, and I haven't touched anything else. Sprayed the switches, pot, and on top the switch and pot. Clean the tube sockets. And I did end up replacing the 6SJ7. I thought I was getting better performance out of another tube. So let's see how this thing works. Let's put a load on there and see if we can get something out of this and see if it's stable. I've let the regulated power supply warm up for about 15 minutes in standby. And now we are on, and I have the voltage control at 0. As you can see, I'm at minus 0.34 volts. Pretty much no matter what you do with that 0 potentiometer, you can't get much closer than plus or minus 1 volt out of 500, so that's good enough. So I'm going to bring up the voltage. Of course, we've changed the capacitors, and I have actually changed the 6SJ7 tube. I've sprayed all the contacts and the potentiometers. So let's bring the voltage up. I have a 5.8K 30 watt load, so that's not going to overheat. Let's bring up the voltage. I'm just going to set it for roughly 100 volts. Let's see how it acts at 100 volts. And this looks to be, what, 20 mils, something like that. But that output looks pretty stable now. Okay, just went down 0.1. But remember, it was going down nice and steady before. I think just changing the caps helped. Oh yeah, this is a lot more stable. Let's bring up the voltage. So this should be around 200 volts. Volts. That's pretty happy. Okay, let's bring her up further. Try for 300. We're really at the limit here, I think. 300 volts, and I'm very happy. I'm around 50 volts. I'm looking at ripple. Boy, the output looks darn clean. Pretty impressed. There is some noise when you do the voltage adjust, but it settles down once you get to voltage. Let's go up to 100 volts. Let's go up to 200 volts. Okay, here's 200 volts. Let's bring it back down to 100. Okay, back down to 100 volts. And I'm down at the 5 millivolt per division scale. It's very good for ripple. I declare success. This is going back to WA1QHQ. Have fun with this beautiful regulated power supply. This is going to be on the bench for another 30 or 40 years.